och istället bara köra en fossilfri kallas istället
för So good morning. Let us start today's lesson. I have decided to live stream. I don't know what is happening with the camera now. Hopefully this is working at home as well. I think I see a bluish light here, unfortunately. But it is visible, hopefully. Okay, so today we want to continue the topic of combinatorics by learning about a very important part of combinatorics called combinations. But if you don't mind, before doing that, let me also give you an example for warming up. And then it's a different problem. These type of problems you need to know how to do. So let me just write this example. What we can do is this. I want you to solve the following equation. Solve the following equation for n. So the equation is this. So it's 2 times p n and 2 plus 50 equals to p 2n and 2. So there are some questions that you really don't need to count anything in combinatorics. This is one type of questions. So here there is a formula for p, n, and r. Do you remember? So we had this formula, the number of r permutations if I have n distinct objects. This formula will be given to you in the formula sheet, and it is n factorial, n minus r, whatever it is, factorial. Okay, and then we want to solve that problem. Okay, so how we should do, we have to use that formula here. So there is nothing to count here. You just want to use that formula and then determine the natural number n. So what we do, for example, one way to do it is just to write the formulas, yes? So p, n, and 2 here, n is the same n, but 2 is playing the role of r. So what happens, this becomes n factorial, and then divided by n minus 2 factorial. And then this is just 50 equals to p 2n and 2. 2n is now playing the role of this n, and 2 is playing the role of r. So replacing them, it becomes 2n totally factorial, divided by the difference of these two numbers, 2n minus 2, whatever it is, factorial. So you just translate this equation into this equation and try to determine n. Yes. So what is the best way to do it, for example? Do you have any idea? No ideas? Okay, so what I do, I expand n factorial so that it can be simplified with its denominator, and I can expand 2n factorial up to a point that can be simplified with its own denominator, yes? And I think this is a standard trick, isn't it? So this becomes 2 times, instead of n factorial, I write n multiplied by the previous number, it's not enough yet, multiplied by the previous number factorial. And then I can stop here because this will be canceled out with what is inside the denominator. And then I have 50. I will use the same trick there. So I write 2n multiplied by its previous natural number, which is 2n minus 1, but that is not enough yet. I go one step forward, so it becomes 2n minus 2 and then I write factorial, and then divided by 2n minus 2 factorial, yes? And then the bad point that actually this factorial part is gone, and what is left for me is just a very normal equation. So I just get rid of these two. And then what I have 2n times n minus 1 plus 50 is equal to 2n multiplied by 2n minus 1. And I see that every number here, in every expression involved here, is divisible by 2. So that would be easier if I divide everything by 2. So then it becomes n times n minus 1 plus 25. On the right-hand side, I will have n times 2n minus 1. Yes? And then that's a very simple equation. Now I have to solve that. So this becomes n squared minus n, and then I have plus 25. On the right-hand side, I will have 2n squared minus n. And then you immediately see that this minus n and that minus n are gone. If I move to n squared to the other side, 2n squared minus n squared becomes n squared. So n squared becomes 25. In general, I should write plus or minus 5. But of course, n is a natural number. This symbol only makes sense if n is a natural number and r is a natural number somewhere between 1 and n. Yes? Otherwise, this symbol does not make sense. So n equals to minus 5 in this context is not acceptable. So the only possible answer is n equals to 5. So sometimes in combinatorics problems, you get a problem that is not related to counting. You need to be able to prove identities. You need to be able to actually solve equation. So let me give you one more example, then we just immediately go through. So example, let n and r be natural numbers such that r is between 1 and n, including 1 and n. Prove that. You want to show that this is true. P n plus 1 and r is equal to p n and r plus r times p n and r minus 1. Okay. So you see that is a combinatorics problem, but it is not related to counting at all. You're supposed to prove an identity. You need to prove that the left-hand side of this identity is equal to its right-hand side for whatever natural numbers n and r I choose, provided that r lies somewhere between 1 and n. So that's also one type of questions that you might get in this topic. Okay, as usual, if you want to prove an identity, it's usually better to start from that side, which is more involved, and try to simplify it with the hope that we can reach to the other side. Yes? So I think that you agree with me. The right-hand side is more involved, so let us start from the right-hand side. Yes? So the right-hand side. And the formula that you need, of course, is given here. Pn and r is exactly this. So this becomes n factorial divided by n minus r factorial. And then I have r multiplied by pn and r minus 1. So n is the same n, but r has to be replaced with r minus 1. So the numerator will remain n factorial as it is, but in the denominator, I will have n minus r minus 1, but factorial. Yes? And then I have to simplify it as much as possible. So if you don't mind, let me just open the pair of brackets inside. So if I remove these pair of brackets, this becomes minus r plus 1. So if you don't mind, let me just clean it here. And then write minus r plus plus 1. Okay. Now, on the left hand side, I have only one expression. On the right hand side, I have two expressions. So the natural way to do, the natural step to take on is actually to make the common denominator. But between these two, what do you choose for the common denominator? Of course, one common denominator is always multiplying the denominators, but that's not the most efficient one usually. So what is the least common denominator or least common multiple between the denominator of that one and that one? What is that? So what do you take for the common denominator?
N minus R plus 1.
Yes, that one, n minus r plus 1 factorial. Do you agree that this is divisible by itself? That's clear. This is also divisible by that one. If you divide it, let me just divide it here. N minus r plus 1 factorial. If I divide it by this denominator, then you know that in the numerator, what can I write? I can write n minus r plus 1 multiplied by the previous number factorial. But the previous number to this, it means this number minus 1. So this becomes n minus r factorial, and this and that are gone. So it is divisible. That is the factor. So this factor should be multiplied in the numerator here. Yes? So this becomes n factorial multiplied by n minus r plus 1. But this to this 1 times, so nothing will change in the numerator. I have 1 r here multiplied by n factorial. So this becomes r times n factorial. And I think now it becomes clear what to do, yes? Because I have n factorial here, n factorial here. So it motivates me to factor it out. So n factorial from the first term, n minus r plus 1 is left, plus from the second term, only r is left. And the denominator is actually n minus r plus 1 factorial. But then you see immediately this r and that r are cancelled. And then I have n factorial. So let me write n plus 1 first. N plus 1 multiplied by n factorial. And in the denominator, let me write n plus 1 minus r. Because I have a look, I am just have an eye here to see what is going on. And then numerator, n plus 1 multiplied by n factorial. Hopefully you agree with me that this becomes n plus 1 factorial. And then in the denominator, I will have n plus 1 minus r factorial. Yes? And now let's compare this formula here. If you compare this with the formula, you see that the only difference is that everywhere that you see n, now you have n plus 1. So that's exactly this formula, but n has been replaced by n plus 1. This becomes what? I hope that you understand. If not, please let me know. This becomes that. Is that understandable, the last step? Yes, and this is exactly equal to the left-hand side. So that is also one type of question. Here you were supposed to solve an equation and find n. Here you're supposed to prove an identity independent of choices that we make for r and n, of course, in the domain of applicability. Is that clear? Okay, but there is one skill that I want you to improve if you like this topic. That would be very fun if you could cook up an argument, a combinatorial argument that you can predict this without algebra, just by combinatorics. Can you imagine a scenario, a counting scenario, that you can count the scenario in 2 different ways? One way gives you this number, and one way gives you this number. But because you are counting the same thing in 2 different ways, these 2 numbers should match. Is that understandable? That's called combinatorial argument. So that's an algebraic argument, completely valid and precise. But I want you to improve your skills if you like this subject. It's important to try to see that, okay, let me set up a problem for myself and start counting something in two different ways. One way, convince myself that the number is this. Another way, convince myself that the number is this. And if I haven't done any mistakes counting the same thing in two different ways, that should be the same, yes? For example, I don't know, you can, so if you have a square, so one, and if you have, for example, some partitions, so one way is to say that, okay, this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 5 times 6, okay? And then you can say that, okay, each row is 5, so I write 5 plus 5 plus 5 plus 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, sorry. Each one is 6. So 6 plus 6 plus 6 plus 6, 5 times, you see? That's very trivial. So you have 6 here, 6 here, 6 here, 6 here, 6 here. One way to calculate the total number is to write 6 added it 5 times. One way is to use the multiplication. So this number should be equal to this number, something like that. But of course, it would be a little bit more involved. Can you imagine a scenario, something like that? I can give you a hint. So for example, assume that you have n plus 1 students and you want to choose r of them and arrange them in a row. Or actually, you have n plus 1 students and you want to have all r permutations of those students. Or let me just use letters if you don't mind. Might be students are a little artificial. Yes. So for example, let us consider these letters with indices. A1, it's a name or it's a name of a person or whatever. A2 up to AN and up, and then the next one is AN plus 1. So assume that you have these people. They are n plus 1 distinct objects. Okay? And then what is your goal? You want to choose r of them and arrange them in a queue line. Okay? In how many ways you can do that? On the one hand, I hope that you agree with me, that is this number. Agree or not? So if I ask you, I have n plus 1 people, and then my goal is to choose r of them and arrange them in a queue line. If I ask you in how many ways I can do it, this is a very standard problem. Immediately you should be able to answer that. This is equal to what? P of n plus 1 r. Is that understandable? This formula takes care of both processes, the choice process and arranging process simultaneously. So that is the answer, definitely. But you can assume that something is going on. So you can assume that I have two. Okay, so let me just stop a little bit. Can you now tell me, how can I count the same thing which gives rise to the right-hand side? Because I have to count the same thing, yes? I can give you a guide, for a hint. So you can say that in R permutations that I choose, for this last member, there are two possibilities, yes? Either that member is in my choice or not, yes? Okay, then. So you see, I have 4 places, R places for the queue line. Because my goal is to choose R people out of n plus 1 people here and arrange them in a queue line. So I have R open positions. Okay, now concentrate here. In the choices that you make, there are 2 types of choices that we make, yes? Either this person is in my choice or not. Yes or no? Okay. So let us consider all scenarios in which this person is not in my choice. But can you tell me how many of these R permutations are there? Yes? No. I have, you see, I don't want to choose these people, this person at all. All my R choices should be done from 1 to n and arrange them in a row with R locations. So what is that number? Pn and R. Yes? So Pn and R. So I am telling you there are two. So here I have R permutations. The total number of R permutations from n plus 1 distinct objects. This is on the one hand. Forget about this. On the other hand, let me divide it into two types of R permutations. One possibility is that this person is not in my choice. So it means that all persons are being chosen from these n. And then I take R from here and arrange them in this row. So this number is Pn and R. But another possibility is that no, I choose that person. Yes, so either this person is in my choice or not. The number of permutations in which this is not in my choice, this is this one. And now can you tell me in how many of them a n plus 1 is chosen? You still want to choose R people, but one of them is already chosen, and that is a n plus 1. So my duty is to choose how many people?
R minus 1.
From P of what?
From P of n.
Yes.
So P of n.
And R minus 1. Okay, yeah. Okay, that's correct. But this person, I told you, I have chosen this person. How many options are available for this person to put them in one of these rooms? R, yes? So it means that I take this person, I have R options available for me to assign a room for this person. Okay, after that is done, so this one of these rooms is occupied. Now, how many room is left? R minus 1 room is left. And how many people are left? How many people? N people are left. And then I choose R minus 1 of them and arrange them in the leftover places. So that becomes P, N, and R minus 1. And then if I add them, hopefully you agree that this will give you the same number. Is that clear? So that is completely a combinatorial argument. I haven't done anything algebraically at all. I am counting the same problem in two different ways. And these two numbers should match if I have done everything right. Is that clear? Yes or no? Yeah. So that's also good to know. Sometimes if you want to, and this is very powerful, by the way, really powerful. Sometimes algebraically, it is extremely hard or sometimes impossible to prove a combinatorial identity. But if you can design or plan a counting problem and count that problem in two different ways, then you can come up with an identity. That I want you to understand. That is exactly at the level of your knowledge. It is not hard. It's hard to come up with the idea. Okay? That idea, coming up with an idea is not easy. It is hard. But if you can come up with an idea, you can prove actually very complicated combinatorial identities. Okay. Any questions? Now I want to go to the lesson today, which is combinations. So far, what we have learned in combinatorics, order matters for us. But sometimes we really don't care about orders. We care about the combination. Yes. So what members are in my group, regardless of the order, in which order. I just want to choose them. I don't want to arrange them in a queue line. Yes. So whenever this happens and order doesn't matter, actually I am facing a combination. Yes. problem. So okay, so for example, let me consider this. Let me consider these letters A, B, C, D, and E. So these are distinct objects. Now assume that I only care. For example, let me just write 3 combinations. What is the meaning of this phrase? I want you to write down all 3 combinations possible. So it means that, for example, 1-3 combination is what? Is A, B, and C. Yes. But in our permutation, you do not stop here. You also permute them below it. So all of those permutations should be considered a distinct object. But here, if you write ABC, or if you write CBA, or whatever you want, that is one combination. So don't bother to write all of them. Just write one of them. Yes? That's the meaning of combination. Okay, and then can you imagine another combination, for example? Let us try to write everything, if possible. Yes? So one possibility is you have to be a little bit organized, otherwise we will lose, yes? And so let me make them closer together. So one of them is A, B. Hopefully you agree with me. I can write D. Yes. The other one is what? A, B, and then E. Yes. Okay. Then what can I write? Okay. Help me to write. I know how many of them should be there. We will come to a formula for that. But can you just write all of them for me?
A, C, D.
Okay, let us be organized. Yes, that is good. A, C, D. That's the way that I wanted to do it. And then
A, C, E.
A, C, E. Yes. And then probably you want to write A, D, E. Yes. So how many of them? 1, 2, 3, 4, 5, 6. Okay, let us see how it works. And then hopefully you agree. B, C, D is one of them. What is the other one? B, C, E. Yes. The other one, B, D, E. Is there any other one?
CD.
C, D. Do you think there's any other one? Let me count. I want to cheat. Yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, there are no more. So these are the only possibilities. Okay, but and there is a notation for that. The notation is a little bit different. So this is P for permutation. Of course, very naturally, you have C for combination, and then you have N and R. In this case, I have 5 objects to start with, and I am interested in 3 combinations. So this means that C, 5 and 3. This is the total number of combinations, 3 combinations of 5 distinct objects. This refers to the total number of R combinations out of N distinct objects. So in this case, if I have done everything right, this answer should be how much? It's 10. Yes? Here, I want you to find a formula for me. And not only for this case. For this case, I hope that you agree I think we have done it completely right. And this is the total number of 3 combinations out of 5 distinct objects. When I count them one by one, I get 10. So C, N, and R means the number of R combinations out of N objects. So we know that in this case, the number is 10. But can you find a formula for me so that you can answer this question mark for N and R? Of course, R should be between 1 and N. Otherwise, it doesn't make sense. I have 5 objects. I cannot choose 6 of them. I have to choose at most 5 of them. That's the meaning. Okay, can you tell me how can I find the formula? I don't know why this camera is blue now. somehow you need to connect this problem to R permutations instead of R combinations. What happens in R permutations? In 3 permutations, if I ask for 3 combinations, you just write these items. But if I ask for 3 permutations, what do? You write this one, but you do not stop here. You go vertically and write all the possible arrangements. Yes. So, for example, you write A, C, B. You write BAC, you write BCA, you write CAB, and finally you write CBA. Okay? So the depth is how much? Is how much?
6.
6. How do you calculate 6 in general? Because if I have R, this is not definitely 6. What is the number then?
3 factorial.
So yes, 6 is actually here 3 factorial. So this means that if I have R objects, the depth would be R factorial. Yes? And then this one, of course, I don't know exactly. Of course, here I know, but let me call it X, which I don't know yet, the number of columns. But below this, I also have the same depth. Yes? So I can start with A, D, B, and I can start with B, A, D, etc., etc. Yes? But when you look at the whole rectangle, what you see is the total number of R permutations. Yes? So the total number of 3 permutations. So the items that are in this big rectangle is P 5R. Sorry, 5, 3. The total number of items that you see in this rectangle is P 5 and 3. All possible permutations, considering everything. But this is equal to the depth multiplied by the width. The depth is 3 factorial. This I don't know, I have put it X, assuming that I don't know. Then I am looking for X. So then X is the previous number divided by 3 factorial. Yes? And I hope that you agree with me. In general, can you tell me what is this? Is the permutations, so the total number of R permutations, but divided by which number? Divided by? Here I have to divide by 3 factorial. So here I have to divide by R factorial. Yes? And then the formula is n factorial instead of this n minus R factorial. And then I divide it by an extra R factorial. And hopefully you agree with me that this combination is n factorial, R factorial goes to the denominator, multiplied by n minus R factorial. So let me write them in one place. This is the total number of combinations, R combinations, the total number of R permutations of distinct objects, of course, are these. Both of them have separate buttons on the calculator. So it might be on the different calculators, you have different symbols, but you will get a button on the calculator that gives that if you give R and N to that, and it will automatically calculate C, N, and R. But for this one, I don't know, for some reason there is a more common symbol which is also used in your book, and I will usually use that, but I want you to know this. They write it like this and then put N on top and R below. So this symbol is equivalent exactly to this symbol. I don't know, for some reason I don't know the history behind that, but this is more common when it comes to combinations. But they are exactly the same thing. But remember, here the bigger number should be the first place, and the smaller number should be on the right. But here the bigger number should be on the top, and then R, and then you read it in this way. You read it N choose R. This is the way that we read that symbol. And that is reasonable because the number of ways that you can choose R person from a group of n people is this number. And if you don't want to arrange them, you just want to choose them, the number is exactly this. Okay, so let us just repeat. When I am allowed to use this formula to count something, whenever I have n distinct objects, I want to choose R of them, regardless of the order of my choice. Whenever this is your strategy, you need to remind yourself of this. Whenever not only you want to choose, but you want to arrange the people you have chosen, the items that you have chosen, then you need to think about this formula. This formula takes care both of choosing process and arranging process. This only takes care of choosing process, yes? So is that clear? But in both cases, n objects should be distinct. If they are not distinct, you need to consider different scenarios and add them up. There is no single nice formula for that case. So is that clear? Yes or no? Okay, now let us try to solve some problems. But before doing that, let me test your understanding a little bit. What do you think, without calculations, what do you think will be the result of this? Don't cheat, don't calculate, yes? So what would be the result of this if I calculate? So how do you interpret this? You interpret this, for example, I have n objects, let us consider n people, and you want to choose n of them. In how many ways I can do that? One way, yes? If I want to take you to, I don't know, to Rome, for example, and I can say that, okay, I want to choose all of them. There is no choice. We can go together. Yes, but let me test your understanding. So this answer is 1. Let us do it algebraically. Do you think it also squares with this calculation? If n and r, both of them are equal, so what happens? It becomes n factorial divided by n factorial, but n minus n factorial. N minus n is 0 factorial is 1 by convention, and when you divide n factorial by n factorial, it becomes 1. Yes? Okay, what is this one now, do you think? What is your expectation about this number? It should be what? N. I have n people. I want to choose only one of them. How many options is in front of me? N options. I can choose either one of them. Yes? Let us calculate it using that. So your prediction is that this is n. Okay. So let us calculate. N1. N choose 1 is equal to n factorial divided by 1 factorial. The difference between these two numbers, factorial. But 1 factorial, I don't need to write it down because that is 1. But instead of n factorial, I can expand it like this and then write n minus 1 factorial, and this one and that one are gone, and the answer becomes n. Yes? But this one, you cannot say anything here. This is not something that you can predict because it's meaningless, but the symbol makes sense by convention. This is also important to know. This means that I have n people and I don't want to choose any of them. So it doesn't make sense. You can say that there's one way, just forget about it and go, yes? But yes, the answer is also 1. But it is not very sensible if you want to interpret it in this. So this is because we have the convention. So here this becomes n factorial, and then this becomes 0 factorial, and then the difference between these two, which is again n factorial. This one and that one are gone, but because of that convention, which we understand it's a nice convention, the answer becomes again 1. Yes? So in any way, if you want to interpret it, that's up to you. Okay. Let me test your understanding about this. Can you predict what will happen for this? Choose n minus 1. What should be the answer? The reason that I am asking these questions because I want to improve your skills about counting. Algebra is very simple for you, but can you predict what will happen without calculations? What is the interpretation of this symbol? You can assume that you have n people. Yes? You want to choose n minus one of them, I don't know, to give them lunch or whatever. Yes? What is the answer? In how many ways you can give n minus one people out of n people lunch? Yes? N number of ways. Can you elaborate a little bit more? Yeah, in other words, if you want to choose n minus one people, okay, to read the name of n minus one people to take them for a lunch, it's easier to read the number of the person we are not supposed to take with you. So the total number of ways that you can choose n minus one person from n is definitely equal. Do you feel this equality or not? This tells me that in how many ways I can choose one person out of n. This tells me in how many ways I can choose n minus one person from n, a group of n. Whenever you do this choice, you are also making a choice for n minus one, yes? If you do this choice, it means that I am choosing the person to do this. So it means that you have already chosen n minus one person not to do this object. So this is a one-to-one correspondence, yes? So this is again equal to n. Okay, so now let us solve some simple and basic problems, okay? So assume that you need one mathematician and one physicist for doing a project. Yes. Now let me make it better. So here, so you have say 10 physicists, and for example 15 mathematicians. Yes. For doing a project, you need 3 physicists. Yes, let me write P for physicists. And you need 5 mathematicians. Yes. And assume that all physicists are qualified at the same level, and all mathematicians also qualified at the same level. Okay? So, in how many ways you can make up this team consisting of 3 physicists and 5 mathematicians? So that's also a 2-stage task, yes? The stage 1, for example, is choosing 3 physicists. And so in how many ways a stage 1 can be done? I have 10 distinct objects. I want to choose 3 of them, and order doesn't matter here for me. The combination of that group matters, yes? And then this becomes choose 10, 3. This is the number of ways that I can choose 3 physicists out of 10. And then in 15, choose 5. I can choose 5 mathematicians from this number of mathematicians. And then what is the answer to the total problem now? Should I add them or multiply them? Multiply them, yes? Because the task is to set up the team. The task is accomplished after 2 stages are done. So that is this answer. And I usually, if you write this for me, that is completely enough. Unless I ask you to give me the final answer. Okay, either you can use your calculator if that's too lengthy, or I'm just trying to test your understanding about calculating these numbers. So if you don't mind, let me calculate one of them at least. For example, choose 10, 3. How should I calculate this? I have to put 10 factorial in the numerator, 3 factorial in the denominator, the difference between these two, 7 factorial again in the denominator. And if I want to simplify that, hopefully you know, you don't really need the calculator here for these small numbers. So for 10 factorial, I write 10 times 9 times 8 times 7 factorial. I do not touch the 7 factorial because it will be cancelled out, but 3 factorial I have to write. It is 6. And then this 7 factorial and that one are gone. 6 to 3 2 times, this is 3 times, and this is 2 times 4 times. So this becomes 120. So you see, calculating this is not that hard even without calculator, and I really want you to know how to do it. Okay. Okay, now let me do some questions about set theory. Probably this is a very abstract way of understanding combinations. Why combinations and sets are somehow related when it comes to counting? Because you remember, hopefully, that in set order doesn't matter. Yes. So for example, let me give you a set A, 1, 2, 3, 4, up to 10. Yes. And I ask you, how many 3-element subsets are there? How many 3-element subsets you can write for this set? If I ask you how many subsets you can write, you can immediately answer. What is that? 2 to the power 10, if you remember. So that is just that only needs the product group. But how many 3-element subsets that I can write for this? Is this a permutation problem or is it a combination problem? This I want you to understand first, yes?
In sets, the order doesn't matter.
Yes, so in the subset that I choose, it doesn't matter in which order I put, the combination of the elements matters. So it means that this is not a permutation problem. That's a combination problem. And if you want to answer that, what is the answer? Can you just tell me? It is choose what? I have 10 distinct objects, but I want to choose only 3 of them and put them in the curly brackets. That becomes a 3-element subset. So that is the answer. Yes? Okay. So for example, let me say, how many 7-element subsets are there? Include let me write it in this way, including 8 and 1. Can you answer this question? So how many 7-element subsets? If that is finished, the answer is choose 10th set. But now I am asking you, this 7-element subset should include both 1 and 8. So what's the answer? So what should I write? First of all, so you need to tell me, because if I just write the answer, it will be clear.
8, 5.
8, 5. How did you come up with this answer?
I just chose number 8, number 1, and put them, and then.
Exactly. So I have this obligation, 1 and 8 should be in my set. So when I open the curly brackets, first of all, I put 1 and 8 in any order that I want here. And then how many is left for me to choose? 5 of them will be left for me to choose, because this has already decided about. 1 and 8 have to be there, but 5 of them is in my hand. Okay, but I have seen some students write 5 from 10. Why 5 from 10 is wrong?
Because you've already chosen.
So it means that if you write 5 from 10, you also give the opportunity to 1 and 8 to be chosen once more. That is not the case. So you have to write 5 and 8. Okay, let me ask you one question. How many of them include 8 but exclude 1? How many of 7-element subsets include 8 but exclude 1? So any answers? Including 8, excluding 1.
8 over 6.
So you mean 8 choose 6?
Yeah.
Yes.
Something like this. Okay. Why is the answer? Why is this the answer?
Because first you pick number 8 and put it in the list, and then you take away number 1.
Yes. So I am supposed to choose 7 elements. One element is already chosen for me, and that is element 8. So I put 8 here. So my duty is to choose the rest, which is 6 of them. But I am not allowed to choose 8 once more, and I am not allowed to choose 1. So 2 of them will be gone. So how many of them are left? 8. That's the answer. So that's a very simple problem. So you see, this problem is very immediately related to the actually combination problem. Okay, let me ask you one more question here. Okay, I want you to give the final number for this problem. Okay, so assume that we have 3 girls, and then we have 4 boys. We want to set up a team consisting of 4 persons, yes? Really, the gender is not important at all, okay? So for this team. And then, in how many ways we can do this choice if there is one obligation? There is at most one girl. At most one girl has to be chosen. There's only one obligation. In how many ways I can set up a team of 4 people from this group of people so that there is one constraint. The number of girls should be at most 1. Don't write it in the combination form. Calculate the final answer and give it to me. I hope that the question is clear, yes, because translating these questions sometimes becomes a little bit tricky. Yes?
What did you have to include a girl, or was it at most one girl?
No, it is written at most 1 girl.
Okay.
So you need to interpret what's the meaning of at most. So what's the meaning of at most 1 girl?
0 or at
1.
the very most 1.
1. So these are different scenarios. So this means that, okay, let us consider there are 0 girls. Because I have to choose 4 people, then in how many ways I can do that? One way, or if you want to insist to write it in that one, you say that I have 4 persons, I want to choose 4 of them. So that becomes 1, yes? Or, this is one scenario. So you can, if you really want to calculate something, you can say this. This is also good to know. I say that from girls, I choose no one, yes? And from the boys, I choose all of them. Or, from the girls, I choose 1, and from the boys, I choose 3. Yes? So this way of writing is good. It's easier to understand, yes? So this is very good. Is that understandable? So if you calculate this number, by the way, this turns out to be 1. intuitively it is very clear for you now. This also becomes 1, this becomes 3, and this becomes 4. So the answer is 13. So in 13 ways, I can do that. Okay, let me write another question here for you. So how can I do that one now? I give you 5 digits, 1, 2, 3, 4, and 5. Let me say 5 numbers. I give you these 5 numbers, and I ask you to write 7-digit numbers. Of course, it is clear that some of these numbers should be repeated because there are 5 of them. I want to write a 7-digit number. What is the total number of 7-digit numbers in which in each we have exactly 1 5? Yes. So I give you these 5 numbers. You are supposed to write 7-digit numbers, but not every 7-digit number is acceptable. We have to have exactly 1 5 in that 7-digit number that you make. So how many ways we can do that now? Actually, this problem is not a good problem because is it related to combinations or it's permutations?
It's
Order
permutation.
matters.
Pardon?
Order matters.
Here, order matters, yes. So let me change it a little bit. So let me. In each, we have exactly 5 odd digits. Not exactly 1 5. In each, we have exactly 5 odd digits. This is also somehow permutation, but looking it from the eyes of combination, I think makes it easier to solve. That is up to you. Okay, let me just wait a little bit for you to digest the problem if you have any answer. Just read your answer in factorial form, in permutation form, whatever you want to. Yeah, this is a good example. Of course, you know that this is not a combination problem. When you want to make a number, the order of the digits matter, actually. Yes?
Göra så en är den största och är det minsta. Då säger jag att n är antalet platser där vi ska lägga de udda siffrorna och r är
Det gör det.
de.
Men det får inte.
Jag gör samma när han gjorde så.
Okay, I want to wait a little bit more. Solve it in any way. Don't get confused. This is the problem.
Exakt, så därför säger jag att det är 5 digits. Och sen 3 siffror. Ja. 5 platser där 3 alternativ kan placeras. Det blir samma svar. Jag lovar. Det här. Och sen multiplicerar du det med. Och då ska du ha 2. Det blir inte bara 1. Nej, för det är 2 siffror som ska fylla upp 2 platser. Så det är 2 över 2. Och det är bara 1.
Vad får inte?
Kalla, skit i det och säga tavlan. Du har siffran 2, du har siffran 4. Du ska välja 2 av dem. Det går bara att göra på ett sätt. Om man inte bryr sig om. Men nu är det permutations också. Det spelar roll vilka plats 2 och 4 är på.
No ideas?
Ja, det blir om man tänker på det ur en combination synvinkel så är det här ändå en rätt tanke. Det är ju inte det. Ja, jag håller med.
So the point of this example is because I want you to see that even though this problem in its nature is a permutation problem, yes, because order matters here, but you can, I don't know, somehow our brain is working more comfortable when it comes to choicing and things like that. If you really want to write such a number, please take my recommendation very seriously. If you really want to write this number, what do? So if you want to write a 7-digit number, it means that you have 7 locations. Of course, these locations are distinct. Yes? 1, 2, 3, 4, 5, 6, and 7. But you want to have exactly 5 of odd digits. So what do you do first? I don't know, might be if it comes to counting, I would prefer to put a mark on 5 of these boxes to denote the places that I am supposed to put odd numbers there. Yes? But this part is not a permutation problem, this choice that I want to make. Because, for example, let us take this mark, this cross, let me take this mark. And I start marking them. Yes? So it means that, for example, I can mark here, here, and then finally there. So this marking means I want to put odd numbers in the marked places. In how many ways I can mark these? So this is one marking. This is different marking or the same marking? It's a different marking. Now my question for you is that in how many ways I can do these markings? So that by looking at the markings, you realize that this is a different marking. For example, here you see that their order doesn't matter. So if I change these two, I say that no, I change these two markings. You cannot recognize that. So just marking them to denote the positions for odd digits is not a permutation problem somehow. Do you understand what I mean? So I choose. So what I do, I choose 5 points out of 7. 5 out of 7. This means that this gives me these markings. Now the markings are fixed. For example, let us consider this mark. Now my task is to fill up these markings with odd numbers from this group. Okay, in how many ways I can fill up this marking? How many ways? I have only one, yes, 3. I can choose, I can put 3 options here. How many options are here? 3, 3, 3, and 3. Yes, so it becomes 3 to the power of 5. I'm multiplying 3 5 times. And then there are 2 leftovers that I have to fill up with the even digits. So how many ways I can fill up this now? I have only 2 options available. So this becomes 2, and then that one also becomes 2. That's the number. Is that understandable? Might be you can find another way. I don't say this is the only way, but that's a very good way. So you just choose, because you see that whenever you want to make a choice, you can think about combinations, not permutations. Here I am making a choice about the locations in which I want to put odd numbers. In this case, when I want to make a choice, that is not a permutation problem, that's a combination problem. So if I ask you what is this counting, this is counting all possible markings. 5 markings out of 7. And when the marking is finished, then I have to order them. And I hope that you agree that the total problem is a permutation problem in which order matters. Yes? Is that clear? That's a good problem, I think. Okay, now let me ask you another question. So, for example, I give you a circle, and I give you 10 points on the circle. So let me count them. Let me write them A1, A2, I don't know, A3, up to some point A10. So assume that you have 10 points on a circle. It doesn't matter how they have organized themselves. Okay? Just 10 points on a circle. How many triangles I can make with these 10 points? For example, one triangle is connecting these 3. This is one triangle. Another one is taking this one and the number 10 and number 2. That's another triangle. Yes? So if you start completing all possible triangles, how many triangles will be there at the end? And how is it related to a combination problem? Do you think it's a permutation problem or a combination? This is very important for me. I want to make sure you understand. Do you think this is a permutation problem or combination problem?
It's a combination.
Why?
Because it doesn't matter which 3 points, the order of the 3 points that you
doesn't
choose
matter.
doesn't matter.
It gives. So for example, this triangle can be viewed as triangle A1, A2, A3. But A1, A3, A2 is not a new triangle. It's the same triangle. So if you start permuting these letters, you are not getting new triangles. These are different names for the same triangle. So it means that order doesn't matter. Yes, the combination of points matters. Yes? Okay, so now, do you want to tell me the answer, Kevin? Then it becomes very simple. Now you told me what is the problem.
Wait, there was 10 points,
10
right?
points?
So then you would write 10 above and then 3 below.
Yes, 10 choose 3. Is that understandable? So that's the answer. As simple as that. Now, why do you think I said that they should be around on a circle? Isn't it true that if I have any 10 points, I just said I have 10 points, how many triangles I can make from them?
Maybe if it's any 10 points, you can make the same triangle with a different set of points.
No.
Or the one that has exactly the same
No, but this is
dimensions.
considered here as well.
Alright, yeah.
But the point is that might be 3 of them or more of them lies on the same straight line. Then they will not give you a triangle. Yes. So for example, if I have this scenario, and then if I take these 3, because combination is actually choosing 3 of them, so that is also one, but this is not a triangle. Yes. But when I say that all of them lie on the circumference of a circle, it actually prevents this situation to happen. That's the only reason. Yes. Now let me ask you one more question. Can you, using combinatorial argument, can you count the number of diagonals of an n-gon? Yes. So you have an n-gon. N-gon is a shape with n sides, for example, and I am asking you about. I consider convex n-gons. What do I mean by convex? So if you have a shape like this, it's not a convex shape, because if I take this point and this point, they are interior to this shape. But when I connect them, some part of this line lies outside. This is not a convex. So, for example, I can have this 1, 2, 3, 4, 5. This is also a pentagon, but not a convex one. Yes, it consists of 5 sides, so it is a pentagon, but this is not a convex one, because if I take this point, for example, and that point, and I connect them, some part of this line lies outside this pentagon. Okay, so I am working with convex pentagon, something like that. This is convex because no matter which pair of points you choose, if you connect them, all points of the line will lie interior to that one. That's a convex polygon. Okay, so now assume that you have a convex n-gon. Can you tell me how many diagonals are there by combinatorial arguments? Yes, so I have. Do you remember we had this in Math 5 when we were dealing with in mathematical induction? I actually proved the formula for the number of n-gon, diagonals of an n-gon using mathematical induction. But in that case, somebody actually told us what is the formula. We proved the formula is correct. But now assume that you want to prove it using combinatorial argument. For example, this is A1, this is A2, this is A3, this is A4, and then you continue A sub n minus 1, and then AN. Now my question is that how many diagonals are there using combinatorial argument? I want to hear from your strategy, the calculation I can do. What is your strategy? Diagonal, you mean that? You know what I mean. For example, this is a diagonal. This is a diagonal. I want to count all possible diagonals of an n-gon. Do you have the strategy?
Yeah, kind of.
Yes, but yeah, please.
So, whichever point you choose, you will have n minus 2 options for the second point that you choose to make it diagonal.
N minus 2 or 3?
Or 3, because you can't choose the same point.
Yes.
But if we make it a combination problem, then it's
Yeah, so pick 2 points. Except the two next to each other, next to the point.
Okay, so no, there's a big difference. So there's a difference here. So what you say, I have n points, I choose 2 of them. So this gives me the total number of line segments. Yes? So it means that I have n points, and then when I write this, it gives me the total number of line segments that I can make up. But the total number of line segments is not my answer because some of them are not diagonals. Some of them are sides. But the number of sides I already know. If I exclude them, what is left for me is the number of diagonals. Yes? So what can I do now? The answer to the problem would be this minus what? N. Is that understandable? Because this will give me the total number of choices that I can make. I can choose 2 out of n. And this is a combination problem because line segment A1, A2 is the same line segment as A2, A1. Because there is no difference between these two, it means order doesn't matter. So that's not a permutation problem, that's a combination problem. But the point is that if I consider all of them, I am counting all line segments, including the sides, which I want to exclude. But how many sides are there? I know there are n sides, so I exclude them. So that will be the total number of diagonals of a convex n-bar. And if you calculate this, it is easy to calculate. And then you can go, if you don't remember, go back to the formula that we proved using mathematical induction. That would be the same formula. So this becomes n factorial divided by 2 factorial, n minus 2 factorial, and then minus n. So in the numerator, I can expand it n minus 1 times n minus 2 factorial, and then 2 factorial is nothing except 2, n minus 2 factorial, it will be simplified, and then I have minus n. And then this one and that one are gone, so this becomes n minus 1 divided by 2 minus n. I can factor an n out, so it becomes n minus 1 divided by 2 minus 1. If you take the common denominator, it becomes n times n minus 3 divided by 2. So that is the answer. Yes? Yes? But the way that you also told me started, that was correct. Yes? You really don't need the notion. Can you interpret how I could come to this formula without the notion of combination at all? That was exactly your strategy, because you're saying that, you see, if I take this point and I want to make diagonals, how many diagonals I can make? If I start connecting this to all other points, I will get how many points? N minus 1 lines. But 2 of them are sides. If I subtract it, it becomes n minus 3. So from here, I have n minus 3 diagonals. From here, I will have n minus 3 diagonals. So from each one of them, I will have n minus 3 diagonals. And I have n of them. So you might expect this is the correct answer. But why this is not the correct answer? Because you are counting each one 2 times. Yes? Because, for example, if I continue this strategy, this line is counted when I am here. It's also counted when I am here. But that's the same line. So it means that every diagonal is counted 2 times. So this is clear that I have to divide by 2. So this is also a correct strategy without using combination. But I hope that you agree with me. Thinking using combinations are a little bit easier. Yes? And that is why probably mathematicians have actually invented the notion of combination. Any questions? Okay, but the topic of combination becomes very important later. So in the next lesson, we will talk about that. So more or less, the idea of the combination is here finished. Any questions? No questions? Okay, thank you very much. We end here.